Hello and welcome everyone. So in the previous session, you know that we were discussing about representational power of neural networks, or we can call them multi-layer perceptrons. So in that, what we discussed, the first thing that we discussed is they are universal. They can model universal Boolean functions. So if you take any Boolean function, you can make a multi-layer perceptron, and then you can show that we can model any Boolean function by using that multi-layer perceptron. And then we also had a discussion about depth versus width, and we saw a lot of implications in that. Today we will see that these multi-layer perceptrons, they are also universal decision boundary approximators or decision boundary modelers. Okay, so these can approach. Basically what I mean by that is that if you take any decision boundary and you can construct a multi-layer perceptron for that, which can model that complex decision boundary. Okay, so let's go with that. So you have multi-layer perceptrons as decision boundary modeler, as decision okay. As I said, by this I mean that if you give any complex decision boundary to this multi-layer perceptron, so it should be able to model it. It should be able to come up with this boundary. So now the first thing, if you have a single perceptron, so this discussion we had earlier, if we have a single perceptron, so with single perceptron, what you can do is, if you have a linear decision boundary, you can model a linear decision boundary with this. So by single-layer perceptron, you can model a linear decision boundary. So how is that possible? So we saw that you can draw a line of that sort. Let's suppose because you know the equation is wixi plus b is equal to 0, or is so when this is greater than or equal to 0, so you have class 1, and else you have class 0. So if you see, if I make, let's suppose in 2D coordinate system, if I consider this to be a line, so I can draw some line like this. So one side, so you have this side, let's suppose, so this side will be class 1 and this side will be class 0. So if you have some linear decision boundary, so you can directly use this. So but you know the problem with that is, if you have a non-linear decision boundary, you cannot do that. So this applies to, if I show you, let's suppose XOR. So XOR was modeled like this. So this was 0 0 0 0 0 1, okay, and then we have 1 0 and 1 1. So these were the 4 points in which we were trying to model these gates. So if you, let's suppose, take AND gate or OR gate, so you simply can do, if you take, let's suppose here, consider this to be 0, so this portion is 0 and this portion is 1. So you have a clear decision boundary. So we have seen this discussion. But let's take the example of XOR. So XOR is 1 in this case, in these two cases, 1 and 2. So now you cannot take any linear decision boundary. You cannot make a linear decision boundary which can sort of model this problem. So how can we model this? Something of this sort. So you have this, and all these things, let's suppose, have a different value. Now you can see clearly that this is a non-linear decision boundary. So now you have to use these multi-layer perceptrons to map these non-linear decision boundaries. So I'll start with a basic example how to now use these multi-layer perceptrons. You basically will use combination of these perceptrons, and then you can come up with the multi-layer. You can come up with the decision boundary. Say we have a decision boundary like this, which is some pentagon. Okay, something of this sort. Say this is the decision boundary, and this is the axis we are working on. So what we can do is, so we can use multi-layer perceptrons. Let's suppose we can take first neuron or first perceptron. So it will give us a line of this sort. So okay, so the line of this sort. So above this, let's consider this is 1, and below this is 0. So we'll keep a threshold. So this is the line which classifies this line. So based on this line, we have now two half spaces. So in the above side we have half space 1, and then at the bottom side we have half space 0. Basically we have this wixi plus bias is equal to 0, one linear decision boundary, by the help of which we are dividing the whole coordinate system into two half spaces. So this can be done with one neuron, because we know this is a linear surface. So now I can have another line. Let's suppose I'll have this line like this. Okay, so again on the let's suppose left side we have 1, and on the right side we have 0. So now this should be, we can model this with and the neuron. And similarly what I can do is I can do it with multiple lines. So now I'll draw some line like this, and then a line like this, and then a line like this. Pardon my drawing if this is not good. But what you can see is you can clearly see a pattern there. Here I'll write some code to show you because my drawing is not good, so I'll show you this code. But all in all, what you saw is that we can use 5 perceptrons. 1, 2, 3, 4, and 5. We can use 5 perceptrons in order to draw these 5 lines. And all these lines are doing one thing. That is, on one side you have class 1, on the other side you have class. And now you can see this. This is dividing the whole space into multiple regions. You have this region, okay, and then you have these closed regions. Let's suppose these closed regions while you have these triangles. Okay, maybe I should draw it. I should draw it by the code so that you clearly see it. Give me a second. So now if you see this, so we have a pentagon here. So in this case we have a pentagon. This is 1, 2, 3, 4, and 5 sides. So what I said is I can use neurons. A single neuron can make one decision surface. So if you see this line, consider this line. Let's suppose the line from here to here. If I draw a line from here to here, pardon my drawing if it's not good, this line, okay, so you will have one neuron responsible for this. So what I said is that this neuron basically will divide this whole space into 2 half spaces, one positive half space, one negative half space. So here we can call this class 1 and class 0. And then what we can do is we can use some other neuron. Let's suppose this red color. So consider this line now. So from here to, let's say, till here. Okay, this is a curved line. I should rather draw a better line. Give me a second. So this becomes difficult on screen. Consider this is the second line. Okay, so this is the neuron which can model this line. And similarly, we can do it for all 5. We can have all 5 lines, and this can be done by all 5 neurons. So 1, 2, 3, 4, and 5 neurons. Let's suppose these are the 5 neurons which can have these things. So now we have to have a threshold. Consider each of the output of these neurons. So output here we have this x1 and x2. So these are the inputs. Okay, so we have, because this is in two-dimensional space, so this is x and y. Okay, call this as x2 and this is x1. Okay, or x and y. So you have this input, and each of this neuron is responsible for one line in the space. Now what you can do is you have these outputs as y1, y2. So let's suppose output of this is y1, output of this is y2, this is y3, y4, and y5. So after this, what we can do is we can sum them up here. Okay, so here we can sum all of these things up, and then you can take these y1, y2, y3, y4. So if this summation, because now you can see clearly over here, so here you will be adding, each neuron will go to this. Let's suppose you have to take this one. So now if you combine the whole network, so you know there are 5 lines. So if the sum is greater than or equal to 5, so here you will have sum greater than or equal to 5. So if that is equal to greater than or equal to 5, you can say that this is the region that we were interested in, the decision boundary that we had. In this case we had pentagon, so pentagon is 5. Here the sum will be 4. Okay, in these pink regions the sum will be 4. Then we will have sum is equal to 3 over in these regions, and then sum is 2 in these regions. Okay, so you can see that here I have also demarcated this color map sort of a thing, where you can see that with 5 you have this boundary is demarcated by 5, and this boundary by 4, 2, 1 accordingly. Now what I can do is I can just say summation of I is equal to 1 to, let's suppose here we have this n, say we have 5 in this case, so yi, if it is greater than or equal to 5, so that's the decision boundary I want. So this is how I can model a pentagon. Is it clear? Can I assume that you people understood this? So this is how I can, if I have a pentagon, I can use this. Let's suppose if I have an hexagon, then okay, now I also want you to see its 3D picture. Okay, 3D picture will see something of this sort. So you can see 3D picture also printed over here. Okay, so this is for the pentagon. So if you see, the pentagon is at the above. So here we have threshold of 5. Okay, then below you see these triangles. You have 4, then you have 3, then you have 2, and then you have 1, and at the bottom you have 0. And we are interested in this, so we'll apply threshold at this spot. The threshold will be this, so we'll apply threshold over this spot. So this is what we want. Now let's suppose if we want to have a surface which is, say, any complex surface. Say I'll just make this invisible. So then let's suppose you had this surface. Now you know you can use multi-layer perceptron. By each line you can do this. Say you have now, suppose something of this sort. You have at the top, you have and the 1. Now this is the decision boundary. Suppose this is the new decision boundary. So what you can do is you can have complex networks. You can have one network for this, one network for this, then combine them together and you can have an output. Let's suppose for this network you can have 1, 2, 3, 4, and 5, and then for this network you have 5 for this network, you have another 5, 1 2 3 4 and 5. And then what you can do is you can combine all of these together. You can combine all of these together. Okay, then you can combine these two things together. Okay, so here you know that this thing will be formed. So with this you have this red pentagon, with this let's suppose you have this orange pentagon, and then once you have this, so you'll have these two pentagons, you'll have red and orange pentagon. Okay, so this is how you do it with a pentagon. And you can have any complex boundary. Let's suppose you have some human, you have a human of this sort, let's say this is the head, okay, and say body is like this. Basically you can have any sort of surface. Okay, what you can do is you can keep on creating decision boundaries. So you can compose arbitrarily complex decision boundaries. So I'll write it. You can compose arbitrarily complex decision boundaries like this. So the only game if you see here is you have to sort of discretize it. So if you in order to discretize, what you can do is you have to take these polytopes. So we call each of these as polytopes. So you divide your figure into polytopes and then you compose these arbitrary functions. Okay, let's consider now we started with, let's suppose this, we started with pentagon. We can start with say this because I want to show you how many neurons can be used, that should be used. So if I take this example again, if I go back to my code window, I'll show you one more interesting case. So here this was with a pentagon. So we can start with 4. So let's suppose I have to model a square. This is how it looks. You'll have a decision boundary of this sort, and then here the sum will be 4, and here it will be 3, and then it will be 2 over here if you see it. So this is also shown on this C map if you see it clearly over here. So when you put the threshold equal to 4, so it will basically only consider this surface, the rest will not be considered in that class. Similarly, now if you see its three-dimensional representation, so this hold the same graph in 3D, so it will look something of this sort. Okay, keep this, remember this, because this we are going to use again. So now again here you will see that this is 4, okay, and then this is 3, and then 2, and then 1. You'll put threshold, so you'll put, let's suppose, threshold over this place, and you will say above than this the threshold is this, and then we'll have this boundary, and below that we don't care. Okay, this is for this polynet. So let's suppose now if we keep on increasing this, if we keep on increasing n, so initially n was put as 4, now I can increase it to 5, pentagon, heptagon, and you will slowly see that the number of neurons will be increased. So if I say 5, so you saw that for 5, we can start it with 6. Okay, you can get something of this sort. Okay, so this we'll have 6 with here, and then similarly we'll have, let's suppose, 7, 8, 9. So where are we going? If you keep on increasing this, if we let's suppose do some 32, so you will see that basically what I'm up to is I want to construct a circle out of this. Okay, because the more number of sides you increase, so this will look more circular. So this portion will look more circular. So if I'm doing n is equal 32, you can see this is becoming something like this. So you see it's almost looking like a circle, but you still know that it has got 32 sides. So this is a polygon with 32 sides, so it is looking like circle. The more we increase this, so if I take n tends to, let's suppose, infinity, if I say some 1000, you'll say that it almost is a perfect circle. It's taking a lot of time. Oh my god, I should interrupt because this is exceeding, so I will go with 64 only. So if you see this, so this is what is happening at 64. Okay, you can see that this boundary looks like a circle. So this over here looks like a circle, and you know that here n was kept as 64, and this is actually a polygon which has 64 sides, but these sides are so small that it looks exactly like a circle. And you know that here the sum will be 64 and then 63, and it will go on. But if you see it in 3D, the important case that is evident is in 3D. So you see this, it drops exponentially. So if you see this graph, so this graph somehow shows that it drops exponentially. So here this is 64, and then slowly it goes down exponentially. Okay, and you what you can do is you can basically take the limit. You can say that this is my threshold at 64, this is what I want. So if I approximate it, so I won't give the proof of that. So here you will see that n, and then after that you will see n by 2, the threshold we have to set. So below this is, so here you will have to put n by 2, and roughly all others are n by 2. So now if I have to compose this, so I have to use these n neurons. So I have to use n neurons. so that I can, let's suppose in this case n is equal to 64, so I'll use 64 neurons and I'll put a threshold of this, so I can approximate the circle. Okay, now basically what this is actually a cylinder. Okay, this is a cylinder in 3D, so I can have a neuron like this, one, okay, I'll make it this side, so I'll have 1 2 till, let's suppose some n neurons. Okay, and what we'll do is, so I'll after that perform an AND operation of these, I'll combine all of these together, so and then I'll say the summation of I goes from 1 to n, if that is greater than or equal to n, so that is the decision boundary I care about. So this is basically a circle. If you see, we get a circle. Okay, how many of you agree that this is a circle if I put this threshold? So if most of you agree that it's a circle, and if the people who don't agree that it's a circle, they should rewatch it and to convince themselves that this is a circle if we do a thing of this. So now we can compose a circle. So how can we compose a circle? So you have, if you take a polygon which has n sides, so you have to set a threshold at n, but I told you that here this threshold is n and this is n by 2. If I add in bias, so if I, let's suppose, add a bias, so what I can do is I can say summation of yi minus n by 2, so that here I'll set a threshold n by 2 over here, and then this will be 0, and this, if it is greater or equal to 0, and this is 1 to n, let's suppose these are the many neurons, so this is what I write, and this will compose our circle. This will compose a circle. Okay, and should be large enough, and should be large enough. Okay, if I have to make a dummy representation, so this will look something of this sort. So you have these n neurons, and then you have one more neuron which AND performs AND of these. Okay, and here is this composition function. So this is the function, and here you will give these values, the values that you have x1 or x2 in this case. So now you saw that we can have a circle. So if you now have a circle, you can break down any of whatever you are given. Let's suppose you are given any complex, you can fill that with circles. So okay, let me just hide this code. Okay, I hope this makes sense to you. Now what I'm saying is, let's suppose you have this thing, you have a complex shape, you have a shape of this sort, say something of this, so you have shape like this, say some boundary of this sort. So what you can do is, you can have enough circles which will fill this, so you can have circles of this sort. Okay, you will keep on filling the circles. Okay, and you know how to construct this circle. Okay, if you have these circles, because you have a network to compose one circle, and now you only need this circle and you can compose a network for that. So if you have these circles, you can basically come up with any decision surface. Come up with any decisions surface with arbitrary precision. So what is the meaning of the arbitrary precision? The better circle you make, the better approximation you can make over here. Is it clear? Is it clear for everyone? So now you saw that we can have a network which by the help of which we can compose a circle, and circle can be used to almost make any decision boundary. Why I'm saying almost? Because you cannot be precise with 100% accuracy. So there will be some epsilon, some very small number which by which we will be a bit off than that decision boundary. Okay, now let's suppose we have to see how many neurons can be used. Now you saw that each of this circle takes almost k is equal to infinite neuron if you have to precisely do it. So in order to fit a decision boundary, let's suppose consider the first example that we did. The example was like this: you had one decision boundary of this sort. Okay, and on top of that you have another decision boundary like this. Now what we can do is, you have to fill this with circles. So you can fill it with circles like this, and for each circle you will have a hidden layer or a multi-layer perceptron. I'll make it very rough. So now you see that for each of these circles you will have, let's suppose, a network. Consider this is a network which composes a circle. Then you will have such number of networks as the number of circles in here. So basically question was, can we just have one hidden layer? So the question I am answering is, can we have one hidden layer to approximate any decision boundary? So is there a possibility that I can just have one hidden layer in my network and I can approximate any boundary? Why am I interested in this? Because we saw the same with the Boolean functions, because we just had one hidden layer, and in that case we could we saw that if we have enough if we have one hidden layer with enough neurons, that is the depth was exponential. So in that case, we could model any Boolean function. So in this case, if you have one hidden layer, so what is the number of neurons? So number of neurons in this, so let's suppose k, and this k tends to infinity. For each of the circle, you need infinite number of neurons, and then it depends how much precision do you want. As I said that k is equal 64, it looked like a circle, okay, but it was not exactly a circle. So the amount of precision that you want, you will have to accordingly increase the width of this neuron. So we have defined width and depth in the previous session. So you have to increase the width of this neuron, width of this network. So the more width you, basically one hidden layer can model any classification boundary. That is the takeaway from this. So takeaway is, so if you have just one hidden layer, so you had these hidden layer, and then you combine these things. You'll combine these things with one. So you'll combine them, and then you will get a surface of the sort that you wanted. This surface can be modeled by using this. So as I said, takeaways, with only one hidden layer of multi-layer perceptron, you can model any decision boundary. You can model any decision boundary with one hidden layer in an MLP. So in MLP, if you just have one hidden layer, so what you can do is you can model any kind of boundary. So we now can make a conclusion that this MLP, so this is basically universal classifier as well. So initially you said that you can model any Boolean function, okay? So now you can say that this is a universal classifier. Universal classifier. The second phase of the discussion. So in the previous session also we did this. So initially we established that using one single hidden layer of neurons, so we can model any type of Boolean function. Then we said, okay, what is the trade-off? So can we somehow increase the depth so as to decrease the neuron? So we want to take this to exponent. Now you can see that clearly that this k is equal to infinity. It tends, like, you have to use a lot of neurons. So here, if this is n, and when it tends to infinity, then only you can model it precisely. Is it clear? The second half of the discussion is that we will see that again, width versus depth. Width versus depth in terms of classifiers. Previous session we saw it in the Boolean functions. Now in this session we'll see it for the decision boundaries. Any questions still here? So now we have to do this treatment of how, if we increase depth, what is the thing that we get? If you remember previous session, we saw that on increasing depth of neural network, what we got is we could decrease the number of computational units, that's number of neurons. So why do we want to decrease the number of neurons? Because each neuron is a computational unit, and it needs resources to perform its computation. So we need to decrease the resources, and that's why we see why not just have one hidden layer, because it uses k tends to infinite number of neurons and infinite number of computations as an inference of that. Now you want to decrease it, so what we can do is we can increase the depth. Okay, I'll take an example. So in the previous class we also did this with k maps, and then we saw a Boolean function and we made reducible form. So in this case, if you again see the same form, now how complex can you make a decision boundary? So in the previous session we saw that how complex can you make a Boolean function. So there we saw that we should not be able to minimize that. So in the previous function we had disjunct normal form. So we said how complex can this DNF be? So I said that this DNF form should be irreducible. So you should not be able to reduce it, because we had a trick. So if you have a disjunct normal form, and then you could use Boolean algebra on that, you could reduce that. And if you reduce that, then you can reduce the number of terms or the number of computing units in here. Similarly in this, so how complex can a decision boundary be? So I'll make a decision boundary so complex that it engulfs everything. So what I can do is I can make again the same. So there we made a checkered k map. So here in the similar fashion, we'll make a checkered decision boundary. So how that checkered boundary will look like is something of this sort. So I'll have lines like this. Consider this as my 2D coordinate space. So I am doing this treatment in 2D. The same applies in any dimension. Okay, this decision surface can be in any dimension. It's not necessary that it will only be in 2D, but for the visualization purposes, I am making it in 2D and sometimes in 3D. So what I can do is I can make lines of this sort. So 1, 2, pretty bad at drawing. Okay, then I will make more lines like this. So these are the lines. Maybe let's increase these lines. I can increase one more. And now what I'll do is I'll make a checkered board like this. Let's suppose I'll start from here. So wherever I color, that means you have to give this is the decision boundary and other side is not decision boundary wherever I color. So I'll color that with orange. So because I want to make it checkered on purpose. And if you have seen previous session, you know why do we want to make checkered. Okay, something like this. I hope you got the idea how I want it to be. Okay, so this is what I want. Now I have to make this decision boundary. If you have to see in this decision boundary, what I can do is I can do this for, let's suppose, these wherever you see colored regions. So I want to make a network which would map this. So we should model this. This is my problem, what I want. So I want to have a network so that it does this. So what I can do is I can take a lot of these. I can take k tends to infinity. I can make a network like this with naive approach. So I can have this, a lot of neurons where let's suppose we have k number which tends to infinity, and I can give this x1 x2 as an input, these, and then I can club these together so as to make this decision. Now the question is, can I somehow reduce it? Can I reduce it? Can I reduce the number of neurons I can use? Okay, so again I'll use this, I'll use the concept of optimal depth. So how can we optimize this? So now if you see this, so now this is made up of lines. If you see whole of this is made up of lines. So what I can do is I can use multiple layer of network. So I have this input x1 and x2. So in this will give me the input, and then I'll model all these lines. Let's suppose this is a checkered board of 8 cross 8, say 1 2 3 4 5. So you have 1 2 3 4 5. I have 5 cross 5. So that's how the checkered board, that's how we got this checkered board. Now in this case, so consider this, I have this n. So I can have 2 layer hidden network. Okay, so by 2 layer I mean we will have 2 hidden layers. So in the first, what I can do is the first layer will be modeling these lines. Okay, it will be modeling all the lines, and then I'll take care of these checkered ones, basically where I have to give the output as 1. So this basically means active. So in this case, this means active. We have to activate our neurons, and this means inactive. So as I said that for these, if you have this n cross n, so I'll make these lines. So these many number of lines. So let's suppose we have these 56 lines, say. So then what we need a layer of we need 2 layer network. So we'll need 2 layer network. So why 2 layer network? So because 1 layer will be used to sort of model each of these lines. So the first layer, so let's suppose first hidden layer will be used to model the lines. And second layer will be used to model the checkered pattern. If you are not able to understand why this, so you should watch this lecture in combination with the first lecture that we I think had in the previous week. So then you will understand the whole story. So okay, so what I'm doing here is we have a surface like this, which is a checkered surface. So this is sort of that, this is analogous to that irreducible DNF. So now what I'm saying is you can have a 2 layer hidden network. So in that 2 layer hidden network, the first hidden layer will be able to model these lines. Okay, let's suppose these are n lines, so you will use, let's suppose, n neurons in the first layer, n neurons. Okay, in the first layer. And in the second layer, what you can do is, a number of these active cells are there, you will use these many number of neurons in the second layer. Okay, the first layer will have a number of lines. So you'll have x1 as input, x2 as input, and then first layer. So what will first layer contain? Number of lines. So if you see this checker, and the second, this will contain the number of active cells. So by active cells I mean, so wherever you see this pattern, wherever you see this orange, and then you can make it like this. Okay, so if you see this region over here, so if you see how many regions, so if you have, say, these many lines, so you have 1 2 something of this, or 1 2 3 4 5 6, you have all these regions. If you can break the cells, you'll have, if you have 8 lines, if you have 8 lines on this side, 8 lines, 16 lines, so you'll have to use 16 neurons. So if you have 16 lines, so that means 8 horizontal lines, 8 vertical lines, so you'll use 16 neurons. So from y1 to y16, so you use these many neurons in order to map these lines. Now you have to do it with a checkered board. So you have, this is x1 and this is x2. So you are using y1, y2 till y16, because this is the number of units. I'm just taking a concrete example. So you had these 16 lines, and now you have to use it for checkers. Now within that you have 16 checkers. Okay, so with this 16 neurons in the first hidden layer, and then in the second hidden layer, let's suppose with this you have basically 40 cells which are active. So if you count the number of cells, I have written it down here. So you'll have 40 cells basically which are active. So in the first layer you'll use 16 neurons. In the second layer you'll use 40 neurons. Call this N1, then N2 till 40, N40. Total number of neurons. If you have a checkered board of this sort where you have 8 lines like this, 8 lines like this, and 8 lines like this. Okay, you have there's 8 lines of this sort, 8 lines of this sort. So what I said is, in total you will have 16 lines. So for the 16 lines you will use 16 neurons for the first layer, and for the second layer, because there will be, because you are making this checkered board, so you will have 40 of these active cells, and then in the second layer you will have 40 neurons. So this is my layer 1, and this is my layer 2, and here we had 16 neurons, and in this case we had 14 neurons. So for such a network, what you use, you will have 40 plus 16 neurons. Okay, and then one neuron to add. So you have in the output you have one more neuron. So add all of these things together. So you have one. So this is 57 neurons in total. Okay, including the output neuron. Okay, now but if you remember previous lecture, this checkered board is something of an XOR. So this is mapping like an XOR. Okay, Asif and Muzaffar were in the class. So can you tell me what can we do? Can we reduce this layer again? Can we do the same treatment for this layer? Okay, just a side note, as I said that this, you are mapping it like XOR. So this checkered board is like XOR, because K-map is, with the K-map we construct for XORs, the same thing applies to the checkered board. So now what I said is in the second layer, so the hidden layer second. So I can again use the property of associativity of XOR, because what I said is in the previous session, if you see that, you had checkered board like this. So let's suppose XOR was mapped of this sort. So you had XOR like this. Oops. So you had XOR like this. So once XOR was this. So if you use only a single hidden layer, so the number of neurons we were using was this many neurons. Okay. Then we said that, okay, if we can use depth of layers, if I have given liberty that you can use deep neural network. So there we saw that you can decrease the depth to 3 into n minus 1. And with this, the number of layers was 2 log to the base 2 n. So this was the number of layers. And this here was the number of neurons. So similar thing can be done in here. So now this second layer can be broken down, because the first layer is for the lines. The second thing, if you see, is that that is checkered, and it is XOR operation can be applied. Then XOR is associative operation. So this thing can be broken down, and instead of 40, you can just use 3 into n minus 1. So if you had to use, let's suppose, n neurons, so you will use these many neurons. So let's suppose if you have to form a grid with 64 lines. Okay, we'll do this treatment. So grid with 64 lines now. Okay, so if you have 64, now you should have 64 feature detectors. So what is the meaning of that? So that means you should have these many lines, and after that you have these checkered. You have these checkered, and how many checkered? How many cells are active there? How many checkered cells are there which are filled? So that will be 544. 544 checkered cells or active cells. So if you use just two layer deep network, so here for this layer 1 you will need 64 neurons. So in this case you will use 554 neurons, and this is like an XOR operation. The total number of neurons will be 64 plus 544 plus 1, I think that is 609. So these many number of neurons will be used, including the output neuron. So but what we can do is we can use 2-gate XOR operation for this. So we can do on this we can have the XOR operation. So now we can reduce it to some more. So and you can do the calculation yourself. And 544, how many number of neurons will be used, and you have to see, I think 512 is some 2 to the power 9. Okay, let's do the treatment of this. So it is roughly of 10 neurons, say n is equal to 10 in this case, suppose. Okay, in this, let's suppose this is 1024, not just 554. So initially it was using these many neurons. So what we can do is now we can use 3 into 10 minus 1, 9. These many number of neurons if we use the XOR operation, that is 327. So 27 plus 64, and that 1 neuron, let's suppose 1 neuron, and this will be roughly in the order of, say, 100, in the order of 100. Okay, now you see the difference, almost 6 times difference. So when you made the network deep, so now you can see that you are reducing it. So all in all, what you can do is, in order to have a network, so you should be aiming to make network a little bit deeper than the wider. So in wider, the problem is that you need exponential number of computational units or neurons, which we call it. So if you are making this network deeper, So maybe you are reducing it, you are using less than this. But still the problem is that in the worst case, you still have to use exponential in order if you are given any decision boundary. Okay, there's a separate theorem which I won't discuss here. We had discussed Shannon's theorem in previous session where I said that you still need exponential number of neurons. So, and if you could prove that I can have a Boolean function with n inputs, and if I have to make a circuit, I can make a circuit with only n computation units, polynomial computation units. You will be able to prove n is equal to np. Okay, so that we did. So what is the summary so far? So summary basically is, so deeper networks are more expressive. Okay, this we saw in two case scenarios. First we saw with the Boolean function, and second with the decision boundaries. Okay, and one more thing that we saw is that MLPs are universal Boolean function modelers. Okay, Boolean function modelers. I'll just write in the short. And similarly, MLPs are universal decision boundary modelers. Decision boundary modelers. Okay, and the third case is, and keep these 3 points in the view. First, deeper networks are more expressive because they can express more, and it reduces our number of complex units, the required number of complex units from a exponential to polynomial. Here in this case, from infinity to some polynomial, but it's not always the case, because I said that Shannon's theorem says that if you have an input function, so you sometimes still need exponential number of neurons. Okay, now one more thing that we have to say is that multilayer perceptrons, they can be used as universal function approximators. That is the third thing in this case. So apart from this deeper thing, so you have multilayer perceptrons as universal Boolean function modelers, and then you have multilayer perceptrons as universal decision boundary modelers, and now you have multilayer perceptrons as universal function approximators. Multilayer perceptrons as universal function approximator. Is it clear so far? Can I assume that you have understood almost? Okay, now you understood 2 points at least. First point was, by using these multilayer perceptrons, I can model any type of Boolean function. Okay, and then you saw that there is practical use of deep, why a network should be deep. And now second thing that you saw is, after this Boolean function, then you can say, if I have any decision boundary with arbitrary precision, I can model any decision boundary by the help of these MLPs. As I said, third thing is, these MLPs are universal function approximators. So why is that? Okay, because you know what a function is. So anything that we do in deep learning, I said you are basically modeling a complex function. So there is a complex function associated with it, and complex function is there which you are computing. Okay, and this over here is called as Universal Approximation Theorem. So all of these 3 statements basically come under Universal Approximation Theorem. Universal Approximation Theorem. And as I said, this is called the representation power of neural networks. So by just giving some more capabilities, I can show you that these neural networks or multilayer perceptrons, we can consider them as like Turing machine. They can act like Turing machines, and you know, anything that is computable can be computed by using Turing machine. So you have your own computer right now, and it uses von Neumann architecture. Just a side note. So what I'm saying is, in order to, if anything is computable, you need a Turing machine to compute that. Okay, and if you know that this thing is computable, so can you construct a machine to compute that? Yes, we can. So what is that machine called? Turing machine. So Turing machine is a machine which can on which you can model any problem. So what I'm telling you, that with some more assumptions with these neural networks, you can show that these neural networks are Turing, that you like Turing machine, they're equivalent to Turing machines. Okay, with some more assumptions. But here we saw 3 things. So you saw that it is Boolean approximator, you can model any decision boundary, and then the third thing that I'm saying is, it can approximate any function. You give it any function and it can approximate it. So why am I saying approximation? Because there will be some error. You will have to have more number of neurons in order to go to the infinite precision. Okay, that we do not want. So now, and all these things, as I said, fall under Universal Approximation Theorem. So what is a function now? So as I said, the things that you do in the world, everything is a function. Everything can be modeled as a function. Any machine learning algorithm is doing nothing but basically computing a function. So let's say you have something is there. So you have a function f of x, which takes some input from Rn and it goes to Rm. So it does some transformation. What is a function? So function does some transformation. It's given some input and it performs some transformation and gives some output on that. Okay, that's what a function is. And it can be a complex function. It can be convex, non-convex, however complex function can be. And you can still have a function mathematically. We can have a mathematical function to describe that process. Now what you want to do is, you want to have a neural network which could approximate this. given any complex function, you want to have a neural network which could approximate. What I mean by approximation, you want to have a function g of x, which does the same thing, which takes an input Rn and goes to Rm. But now you cannot tell me with sure that I can exactly come with the same function. You can approximate it, because as I said that you should then have infinite computational power, but in reality we do not have infinite computational power. So what I will say by approximation is, so if I take f of x and then this g of x, so this g of x is modeled by, this is bineural network, so this is bineural network or by these multilayer perceptrons, and this is the real function, the actual function that the underlying function is. Okay, now if I subtract these two things together, okay, so I should not get error more than epsilon. So the error that I'm computing error, so this should not be more than epsilon. So epsilon, this is the precision value. How much precise do you want it to be? Okay, so this is desired precision. I can write this is desired precision. This is what universal approximation theorem says. So it says that if you have a function, f of x, so which goes from some Rn to Rm, so this is its domain and this is its range. So it goes from here to here. It does some transformation. So you can construct a neural network of this sort. And if you take this, if you take the difference, if you take how much error will that neural, you can bound that error. So you will have this desired precision. So this is precision. So this is what universal approximation theorem says. Okay, there is a very involved proof which we can also do, but I'll leave the proof as an exercise to you people. But still we can construct some sort of constructive proof is there, where I can show you that how can you approximate these functions. Is this theorem clear? Is this, at least this part, these three equations clear, which are on the right and on the screen? So if you understood this, now what I am saying by this is, let's suppose I am constructing any function. So for the visualization, I will make very simple function. Let's suppose this is a function which is a non-convex function. So we'll define what non-convex function in coming days. Function is of this sort. So this is my function f of x. It takes an input and transform that into an output. So what I'm saying is, now I can approximate this function. Okay, how can I approximate? If I come up with some function which is called tower functions. Okay, so if you come up with functions of this sort, so you'll make a tower like this. Let's suppose some tower like this, and then you will have another tower like this. Then you will have another tower like this. Okay, you see that I am almost trying to approximate this function, and you will fill whole of these things. I want to show you the visualization of this so as to make it more clear. So if you see this over here, so now I can show you the number of towers. In this case is 11. If I increase the more number of towers, so what I can control is these are my towers. So these are the towers I have. Okay, this is my function. Say this is the function I want to approximate. Okay, and these are the towers that I want to make. So in this case I have 11 towers, and now these towers, the difference is that they have difference in the height. Okay, they have difference in the height and difference where they're placed. So if you see on the x-axis, these towers are placed at different positions, and then they have different heights and they have different directions as well. Let's suppose this is in negative direction, this tower is in positive direction, it's a little smaller. So if we talk about this tower is a little bigger. So now if you keep on increasing these towers, you will have better approximations. So if I increase this number of towers, say I'm increasing this, so you are seeing this approximation is almost becoming almost accurate. So the number of towers, the more number of towers you have, the better approximation you have. Okay, so this is, so basically what I now want is, I want to construct this tower function somehow. So can I come up with a neural network which will give me access to this tower function? This is what I want. So this is my tower. Okay, everybody clear on this point? So I showed you one construction. I showed you that if you have a function, so let's suppose I have any function f of x. So if you can give me some towers of this sort, which I can place at different positions on this x-axis, and then I can control their length, I can control the height that they have. Okay, and then I'll place them at appropriate positions. I can approximate any function. So this was in case of R2. So I can similarly extend this same concept to any dimension. Okay, if you're clear on this, then I can move on to the tower constructing function. Okay, so if you are clear with this, now I need to basically make this tower function. So how I can make this tower function? So I need know that, so my single layer perceptron, so it is, I can have an activation function, it can be sigmoid, it can be threshold function. So I can make something of this. So let's say it's a threshold function, I can make something of this sort. So threshold is something like this, it is 0, and then after threshold it is 1. So this is my threshold function. You know, if this neuron is the neuron which is sigmoid neuron, so you can have something of this sort. Okay, where you will have almost the same curve, but you want a smoothened version of this. So this was threshold neuron, and this in case was sigmoid neuron. In our case was sigmoid neuron, because we want that smoothness in the curve. So in this it was an abrupt jump. So if I can use these neurons, if I can use aggregation plus this activation, and I can come up with this tower function, basically I want a function of this sort. Okay, and then I can control its height, then I'll be able to approximate any function. Okay, let's see how can we do that. Consider we can do it with both. We can do it with threshold as well as sigmoid. Consider with threshold, let's suppose. So say you have this T1. So you have T1, this is one neuron, and then you have this T2, this and the neuron, and now you have this input X. This input is X, and let's suppose this input is 1 and 1. Okay, now what we can do is, say we have the addition function over here, something of this sort, and you are adding these things up. Okay, now you will adjust that this is 1 and this is minus 1. Okay, this is the construction of the network. So if you see how will this T1 behave, okay, because the threshold logic is this, so here you will multiply it 1. So once you give this one input, because it is thresholding, so you will see something of this sort. Okay, after this T1 you have this T1, and then T1 will give this one input, and with this T2 will be similar, but with threshold this. So T2 will again look like the same. So you can make it with the sigmoid functions. So when you add these things up, because here you have 1 minus 1, you're basically subtracting one function from the other. So what you can see is that, so before T1 everything was 0, okay, because no input, and once you start with T1, so you'll have threshold like this. So between, basically from this constraint, what I'm saying is between T1 to T2 you'll have output 1, and for the rest you'll have 0. So this is my f of x. So this is the construction, this thing over here. Okay, I'll make it more clearer. So I want you to know that we can have such a network. So this is that network. Okay, I can prove it to you by showing visualization. So I'll make a neuron. So I'll make one neuron. Let's suppose T1. I'll make another neuron T2, and I'll combine their input. How can I combine? I'll subtract them. So that's why I'm giving these weights. Okay. So what I can do is I can come up with this function which I will call tower function. Okay, I can do this with, let's suppose, sigmoid neuron, with threshold neuron, whatever neuron. I'll show you a construction of this sort. So basically I'll have two functions, and then I'll adjust them in such a way so that it makes this tower function. Give me a second, I'll show you the visualization. Okay, so this is the diagram. So here we have this x as an input. So this is my input x, and I will replace this h11 and h12. The earlier one I showed as t1 and t2. Now I'll use actual neurons. So now you have weights and biases correspond to this, and weights and biases correspond to this. So you have w1 and b1. So you have w2 and b2, and then I'll combine these two things together. So I'll subtract these two. So h11 and h12. So what I can do is I can subtract these two things. So I can have a neuron over here. So what I can do is I can write 1 and minus 1, and then I'll give the output. This will be my output. Okay, you know that this h11 and this h12, these are sigmoid neurons. Okay, these are sigmoid. So I'll just remove these. These are my sigmoid neurons. So you know how sigmoid behaves. So in this case, I can control w1, b1, and I can show you h11. And again, I can control w2, b2. I can show you h12. Okay, let me do that. So let's suppose right now, if you see, everything is 0. So you see these things on top of each other. So let's suppose if I control this w1, you said that you see this sigmoid. Can you see it? And then similarly, I can do with this w2. So this basically is controlling this. So what is bias basically? I say that bias is shifting left or right. Okay, so this is controlling the curvature. This w1 is controlling the curvature. How much curvature you want. If I go w is equal to infinity, you'll see it is almost like step function. Okay, this controls the smoothness. How much smooth function do I want? So if you see this is the smoothness of the function. So if you go to w is infinity, in this case w is 100, you exactly see the step function. So now I told you that bias b, it controls basically the shift. So if I see b1, I can show you that it shifts. So it will go left or right. Okay, these are the two knobs or two dials which I can control in order to control this function. So let's suppose now this is the function. Similarly, I can do it with b2. I can say this is the function, and now b2 I can just shift it. I can basically control the width. I can control the width and height of this tower. And now I have to show you this. So if I combine these two, so how can I combine these two, h11 and h12? So it will give me h21. So this is equal to h11 minus h12. Okay, so I'll subtract these two things together. So then it will be something of this. Okay, now if you see this blue curve, I think this is black. So the black one. So if you see the black one over here, so you can clearly see that. So this is the tower function that we wanted. Not with the exact precision, so but this is like a tower function. Okay, again to show you, I'll just remove other two curves. Let's suppose I'll click on these things. Okay, I think this is not hiding, but anyway, you got the point. So let's suppose if I control this, so you can see I can control the tower making. I can make it negative, I can make it positive, I can make it small, I can make it big. Okay, I can control everything. I can control the width by using these dials and knobs. Okay, I hope you are able to see it. Are you people convinced that I can just have two of these sigmoid neurons to come up with this tower function? Okay, now what you saw basically is, I saw that I had these two neurons. So I had neuron 1 and neuron 2, whichever neuron it has. I had aggregation or nonlinear function, then I have linear function and a nonlinear function. So which I made, usually neurons were made like this in the previous class. So this is our aggregation or linearity, and this H was our hidden output, or we called it nonlinearity. Okay, so this was the neurons like this. I said we have weights and biases, W1 and B1. So you have W2 and B2. So this was the input given. Okay, and 1 and minus 1. So I said that if you control these W's and biases, so you can come up with this tower function. So what is this tower function giving us now? If you give me any function in 2D now, so any function that you can give me, so I made that over here. So I can make these towers. So because you have this tower function, okay, now you know the construction of this tower function. So if I have to approximate, say, a function like this, okay, a function is something like this. So what I can do is, I can come up with this tower. So I can say, okay, first tower should be something like this, and second tower should be something of this sort. Okay, these towers should look like this. And you know that I can come up with each of these towers. Okay, something like this. And you know each of this tower can be constructed. Let's call that tower making function by tower making network. Okay, this was over here. So this is that tower making network. Let's suppose this is the output. Okay, and this is my tower making network. You saw this in, now you saw this thing in 2D. Now the same thing can be done in 3D. Okay, same thing can be done in 3D. So you can again have these neurons, and then what you can do basically is you can have, now this sigmoid, when you saw this sigmoid was something of this sort. So this sigmoid was in 2D. Now you know how does the sigmoid in 3D look like. So okay, you will see that will be something of this sort. So if my artistic work is a little bit better, I hope that you got the point. Basically that you will see that sigmoid in this, and you can construct this sigmoid again, and you can have some other sigmoid of this sort. Okay, some sigmoid like this, and this will be a layer, basically a layer. Okay, I'll show you that in also if I found that visualization. But here what I'm saying is that you will get a tower of this sort, then you'll get a tower like this. Okay, but this tower will be in 3D. Okay, something like this. Okay, here and here. Okay, but this is open on both the sides. Now you just don't need two sigmoids only, you'll need 4 sigmoids. So what you can do is, again, you will have to have 2 sigmoids on this side also. Okay, so you should get this point, you should get a hang of this point. So what I'm saying is, when you have 2 sigmoids, and then I'll show you the visualization. So you have this sigmoid 1 and sigmoid 2. The output will be something of this sort. So you will have one sigmoid and other sigmoid. So you can make output of this. But this portion, so okay, the portion that I'm seeing like in and out, that portion will be hollow. But I don't want hollow. I want the things to be covered all the side. Why? Because I will be constructing a function of this sort. Let's suppose I'll have a terrain. So that terrain will have values like this. Okay, so that will be having values of this sort. Okay, something like this. This will be a 3D terrain that I showed you once we were looking at the gradient descent. So you should be now able to visualize these things. I have terrain like this. Okay, and this is some 2D surface, let's suppose. Okay, now how can I fill this? Now I cannot fill this with this tower function. So now I need 3D tower function. 3D towers will be something of this sort. So I can have 3D tower like this. Okay, I can have 3 towers like all over. So I hope that you are visualizing the thing. So you have, consider that you have a surface, 2D surface. Now that surface is like hills, the hills that you see. Okay, you have a 3D surface. You have like a surface on 3D now. That will look like hills and valleys. And now you have to approximate that. You won't use this 2D sort of tower. You will now use 3D tower. That tower will look like, as I said, it will look something like this. Okay, and you will fill this whole surface with these towers. Can you visualize these things? Yes, give me a second, I'll take your question. So what I'm saying is, consider this now, this is a terrain now, or the manifold which we spoke about. So when we were seeing that gradient descent. Okay, every function, if I have that function, if I have to plot that in 3D, so you will see some hills and valleys. Now how can I approximate this? I will have to have a tower in 3D. This tower will look like this. The tower will be something of this sort. Okay, this will be my tower. So initially in 2D I had tower like this. Okay, and I had to approximate tower function. Now what I'm saying is, the crux is that if you take these sigmoid functions, you can have one sigmoid of this sort, you can have another sigmoid of this sort. When you combine these, you will get something like this. Okay, something of this sort. But it will be hollow from two sides. It will be hollow from from in and outside. So what I want is, now I want more 2 sigmoids so that I can just cover them up. I can come up with this one more tower and then I can put them on top of each other to make this. Okay, let me show you the visualization to make it clear. Before that, I'll take the question. Yes, please. So I hope you are able to see this picture. So in order to facilitate your visualization, I am saying consider this as 2 classes. Let's suppose you have this green class and you have this blue class over here. So now you want to separate them. So now if you see the surface will be something of this sort. So this is our manifold that you can clearly see over here. Okay, so everything that is under these values, so this will be categorized as this blue or whatever color is this. So other than this green over here, so this is on the surface. So you see that this is the manifold. Okay, and I want to learn this. So how I can construct this function? So I said that let's come up with these cuboids. So cuboids will be something of this sort. So I'll have cuboids like this. Okay, I'll fill whole this with cuboids. Okay, starting from, let's suppose, this portion over here. So you will have a cuboid like this. Okay, and then you will have cuboid in this. So you will fill whole of this with cuboids. Now this 2D tower functions are they won't suffice, but with this you can have these cuboids. And now you can sort of extrapolate this visualization in ND in any dimension, but we can just visualize in 2D and 3D. So here in this case, if you saw, we had a function in 2D like this. So we had these tower functions, and then in this case, in 3D case, so we again could visualize that we have cuboids. Now after cuboids you have nothing, so, but you still should be able to sort of visualize. I'm sure exact visualize. So you still say, if I take n dimensions, so what is actually happening? Actually there is a function, there are smaller building blocks by the help of which I can approximate the function. I hope this is clear now. If you see this was the 2D tower functions that we saw. Now I am showing you this in Desmos. Okay, and I can control this. Okay, these are all the functions that I had. So this was my function. So I can control this, I can control all of these things. Okay, if you see this y1 over here, that's clearly written as sigmoid. So this y1 is sigmoid. Okay, and this y2 is again the sigmoid, and this is y1 minus y2. The construction I showed you. This was the 2D case. Now in order to go to 3D case, okay, in order to go to 3D case, I also have a 3D case written over here. So now this is my sigmoid. If you see, this is one sigmoid. Okay, I'll show you this. I can rotate this. Good. Okay, what I can do is, let's suppose in this case I have 3 parameters, w0, w1 and w2. So now we'll see the effect of these parameters. So if you clearly see over here, this I can put this w0 is 0 and w1 is this. So w2 that you can see over here. So if you have, oops, I don't want to rotate it like this. This w0 is basically this bias. So bias will shift it. So if you see, bias is able to shift it. So this is how sigmoid in 3D will work. So it also did it in the same was happening when we had in 2D case. We had this bias B, so it was helping it shift. Okay, same case is here. You can shift these sigmoids by using this w0. Okay, and then if you see this w1, so w1 right now is 0. So this will shift it like this. So you see, like from in to out. So can you see it? So it is helping it rotate on that xy plane. Okay, you see like this. Okay, I am increasing the values of w, and you are seeing. So I am putting it 0 so as to clearly see it. So here if I put it like 0, so this is looking like this. So you saw what is bias doing? Bias is shifting. How is it shifting? It is shifting it on, let's suppose this is my y-axis, so it is shifting it in y-axis. So it is helping it to shift to in y-axis. That's what w0 is doing, or bias is doing. So what is w1 doing? Okay, so w1 basically, it is trying to shift it on the xy plane. So it is rotating it like that. So if you now see this w2, okay, so w2 will see how much smoother do you want it to be. That is what we were doing. Look, so how much smoothness do you want? Okay, you can have curve like this also. Okay, so if I take this almost, if I increase the w2 to infinity, it will make it like a step function. Okay, w2 is trying to make it step function. So wy is controlling this axis. So if you see this axis, I can make sigmoid like this. If I rotate, you can see sigmoid is like this. So I need to increase the w so that I can totally make it in, let's suppose, y-x plane in some other quadrants. Okay, but I want to keep it 0 so that it is better visually. This is, oops, pretty hard to control at 0. So this is how it looks. Okay, now this is one sigmoid. If I show you, this is one sigmoid. And another thing is, this is another sigmoid. Okay, now I can do the same thing with that sigmoid also. Can you see it? I can do this thing with a sigmoid. Okay, I will put this w0 at 0. And if I combine these two things, you know, I'll get a tower. So how will that tower be? So here I have not written that. Okay, you have one more graphing calculator that's called, I think, GeoDesk or Geographic or something. So there you can also clearly see that you can have a tower like this. So you can have this tower. Consider only this. So here, don't consider these things. So you'll have tower like this. So you'll have tower of this sort. Okay, something of this sort. How many of you can imagine this now? So now by using these weights, biases, you can control how my figure is looking like. But you saw that this is looking hollow. So if you see, this is hollow. So inside this is hollow. So from here to here, this is hollow. So for that, I need more neurons. So I need more neurons for this. So I need more sigmoid neurons so that I can have something of this sort and something of this sort. So you know how will that look like? I told you once when we were discussing today's lecture, I told you, you have to remember one thing. Okay, you have to remember that picture. So I'll show that picture now again. I'll show you that picture. Give me a second. So if you see, these are the two tower functions. Say if you consider this, so from this one, so here, 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 and here. So if you see that this is one tower function. Okay, because but it is hollow inside. So you see from here and here this is hollow, which I showed you on the visualization. Okay, now the second tower function is this. So this is my second tower function. So from here, here to here, this is my second tower function. Okay, if you can imagine it in your brain, if you can rotate it in your brain. So I am now combining these two tower functions. So how I am using 4 sigmoid neurons. This is in 3D. So now you see different regions are getting formed. Okay, so how are these different regions getting formed? If you see, so function over here, so here and here, and then you have function of this sort again, something of this sort. You see here the value is in 1 and 1, so that's why it's adding up over here. It's becoming 2. Okay, sometimes it's cancelling on these portions, it's becoming 0, and in these portions it's becoming 1. So the threshold here, so this is becoming say 2, and this is becoming I think 1. This is 1 and this is 0. Okay, don't want to go get on this demarcation. Okay, I'm just showing in terms of neurons. So if you can imagine that if you see this, if you see in the 3D, this is one tower function. Okay, this is one tower. And but then if you see, if you can imagine this, so from this, and then this, like it will be like this. Okay, this and the tower. So now you're combining them together. So if you're adding these two towers together, you're getting something of this sort. Okay, and you are only interested in this portion because all the other portion you're not interested. You want this tower, so you'll put threshold over here. Okay, and because you are interested in this tower, this is the tower that you're interested in. How many of you are able to visualize this? The question here was, if we do something for smaller dimension, can that also be applied to the higher dimension? Okay, so generally what you do basically is when you do these problems, so as I said, if you have a linear surface of this sort, okay, so if you make a network which can map this linear surface, it will not apply to a non-linear decision boundary, something of this sort. Okay, you'll have to change the network weights and biases. So but usually when you have these networks, you'll have billions and trillions of these weights and parameter biases. So you are mapping actually a function. Let's suppose if you have some 100-dimensional cost function which you have, the inputs you have are in 100 dimension. Okay, so you are constructing a function which of 100 dimension. So in 1D a function looks like this, and you can map this function. In 2D I showed you it looks like these terrains and these mountains, valleys, something of that sort. But 100 dimension you cannot imagine, but you still know that there is a function which roughly is in 100 dimensions. Okay, similarly in this case what I said is, when I have to make this tower function, okay, coming back to this tower function, I used 4 sigmoids. So each sigmoid was in lying in 3D. We have 3D sigmoid. So now if you have this sigmoid, so this and this is one sigmoid. Okay, so this is basically this tower is constructed by 2 sigmoids. So one sigmoid is from here to here, and then from here to here we have another sigmoid. Okay, so this is constructed by 2 sigmoids, and this tower is constructed by 2 sigmoids. Now after overlapping these things, so you can see that a figure of this sort will be, you will get a figure of this sort. So here the sum will be 2 if the threshold is set at 1, so 2, and this will be 1, and these will be zeros. And then you will say I need this tower. You set a threshold like this. If it is greater than or equal to 2, so that means threshold will be this. So once you set the threshold at this place, so you will say that I only need this tower to approximate the function. Okay, I hope you got some clarity. So in this again, remember that we need more sigmoids, because we need 2 sigmoids to map this function, to map this sort of a tower, and then 2 to map this sort of tower. And then when you combine these things together, so you get a tower function, and then you put a threshold over here so as to get this. Okay, I'll make again a diagram. So what you do is, so you have something of this sort. So you give inputs, say x1 and x2. Initially you had just one input x, so now you have x1 and x2. So I'll remove this code window now. So once you give this, so this x1, based on this you will form one sigmoid. Okay, based on, let's suppose, this x2, you'll form another sigmoid. Similarly what you can do is, you can again form more sigmoids like this, and this will be more sigmoids. And these 2 sigmoids will give rise to, like if you combine these 2, you subtract them, and you subtract them over here. So they will come up with tower function in 3D like this. Okay, some tower functions like this. And then when you add these 2 things together, so you add these things and then you get that tower function which is something of this sort, and then you have this, and you basically just want this surface. Okay, the surface basically what I showed you. So you have this x1, and then you can draw these connections howsoever, and you can also add the bias howsoever bias you want. Okay, you can add these bias, but all in all what you have a 3D sigmoid like this, and then you have another 3D sigmoid like this. So you subtract these two things and you get a tower function in 3D, but that is hollow. Okay, from in out, that's hollow, which I showed you. And then again you do it with x1 and x2 again. Okay, you get two more sigmoids. They have different weights and biases, so here the weights and biases are different. Okay, this is my weight, and then I can add one more, I can add bias with 1. So here this will be my bias. Okay, similarly this will be one sigmoid, and then you will have another sigmoid, again subtract, you will get some other hollow function of this sort, and you will superimpose them and you will add them together, and then you will get a function like this which I showed you, and then you will put a threshold over here. Okay, and you will say this is the tower I am interested in. Okay, you will, once you put threshold, and you will approximate this. Similarly, in case of 2D, I had function only x, I had x input, only one input, and I had two neurons. So one sigmoid was like this, and another sigmoid was like this. So you had one sigmoid and you had this sigmoid. Okay, so what you then do is you subtracted these things together. Okay, you subtracted, and you got something of this sort. And this was in 2D. This was my x, this was my x, and I can also put a bias. This bias is this one, this is 1. This is my weight, and this is my bias. This is W1, B1, this is W2. Let's suppose B2. W1, B1, and this is my final function. Okay, so here I showed you by construction that if you have any function, so you can approximate that by using those tower functions. And I showed you a neural network which can create towers. Tower creator. I showed you a construction of tower creator. Okay, this now shows you the representational power of neural networks. So how powerful are these neural networks? You can clearly see that you can have any Boolean function, and you can model that Boolean function. You can have any decision boundary, you can model that decision boundary. Now you can have any function if you want to approximate that. Here, focus on the word approximate. Okay, you won't be able to exactly show that. Okay, the better approximation you want, you have to add more number of computation units. Okay, so that's why here we'll more think on approximation rather than exactly modeling, because we want to give that epsilon precision. Okay, to that precision, that if we take that f of x function, and then if you subtract it with g of x, okay, if you take modulus, the error basically that should be less than this epsilon. This is called a desired precision. We want this much precision. So we saw these three things, that it can approximate any Boolean function, any decision boundary, and then it can approximate any function. Then we again saw that we have a network can be wider, and it can have more depth. So we saw that this depth network, the network containing more depth, is more expressive. Okay, so I'll stop recording over here, and I'll take your questions if you have any.